Let us continue our discussion in Chapter 2, which is the transformer with losses but no magnetic leakage. So we will consider two cases. First is when such a transformer is on no load and when it is loaded. So transformer on no load. In our previous discussion, we assumed an ideal transformer such that one is which there were no core losses and copper losses. But practical conditions require that certain modifications be made in the foregoing theory. When an actual transformer is put on load, there is an iron loss in the core and copper loss in the windings, both primary and secondary, and these losses are not entirely negligible. Even when the transformer is on no load, the primary input current is not wholly reactive. The primary input current under no load conditions has to supply the iron losses in the core such that hysteresis and eddy current loss. Number 2, it has to supply very small amount of copper loss in primary only because there is no copper loss in secondary as it is open. Let us consider one electric transformer with only core losses, which means it has only core loss but no copper loss, and no leakage reactance transformer. When an alternating source is applied in the primary, the source will supply the current for magnetizing the core of transformer. But this current is not the actual magnetizing current. It is a little bit greater than the actual magnetizing current. Total current supplied from the source has two components. One is the magnetizing current, which is merely utilized for magnetizing the core, and the other component of the source current is consumed by compensating the core losses in the transformer. Because of this core loss component, the source current in a transformer on no load condition supplied from the source as source current is not exactly 90 degrees. Lags of the supply voltage, but it lags behind the angle theta is less than 90 degrees. If the total current supplied from the source is I0 or the no load current, it will have one component in phase with the supply voltage V1, and this component of the current is IC or the core loss component. This component is taken in phase with the source voltage because it is associated with active or working losses of transformers. Another component of the source current is denoted as I mu or IM, magnetizing current. This component produces alternating magnetic flux in the core, so it is wattless, means it is a reactive part of the transformer source current. Hence, your IM magnetizing current will be in quadrature with B1, or it is perpendicular with B1, and in phase with alternating flux, phi. Hence, the total primary current in a transformer on the no load condition is represented by no load current is equal to vectorially added the IC core loss current plus the magnetizing current. Equivalent circuit of a practical transformer at no load. So we will consider two things when R1 and X1. So R1 is the resistance at the primary, so 1 for primary. X1 is the reactance for primary, and when R1 and X1 are not considered, draw the vector diagram. When R1 and X1 are considered, draw also the vector diagram. So this is the equivalent circuit diagram of a practical transformer when our load side is open or no load. So this is our X1 and R1. IG is the generated current. Of course, it is from our voltage generated, V1, or the input voltage. We have here the IN, the no load current, and it has to supply the copper resistance here, the winding resistance, which has a current of IC, and also the magnetizing reactance, inductor, and it has a current of IM. This is the induced EMF at the primary, the number of turns at the primary and secondary. E2 and V2 are equal, so open. There will be no current flowing in this side kasi it is open. So I2 is equal to 0, and also I1 is equal to 0. Dito lang mag-flow yung current. So IG will be in series with IN. There will be the same current flowing in R1, X1, and also in this branch. So when R1 and X1 are neglected means we will set our R1 and X1 to be 0. So straight line lang to. Walang R1 and X1. So what will be its vector diagram? So E2, since E2 is open and V2 is open, it is equal to the induced EMF at primary. They are at the reference point. So our reference here is the x-axis. And magnetizing or the flux is perpendicular to our reference, which is 90 degrees, equal to 90. And it is in phase with the magnetizing current. Our copper loss current is in perpendicular also with IM, and it is in phase with the input voltage V1. E1 here is the negation of negative E1. So nandito yung negative E1. IC is in phase with the negative E1 and the input voltage. So the resultant of IM and IC is the no load current from KCL equation from your circuit. We'll have your KCL here, and we will consider it in vectors, not in scalar kasi may inductor. So IN is equal to the sum of IC vectorially plus IM. So we will get this vector diagram. The sum of IM and IC. Okay? So this one will be this angle will be your angle theta. The angle between the voltage, input voltage, and the no load current. Remember, power factor is the angle between current and voltage in your circuits too. So power will be equal to input power or total power. PT or P1 is equal to V1 multiplied by IN cosine of theta. Okay? We can also solve IN using what do you call this one? Pythagorean Theorem. So, adati, this is 90. You can solve IN using Pythagorean Theorem. So, that is IN equal to square root of IM square plus IC square. Okay? So, katawa, you can solve also when IC is unknown. It is equal to arc sine of opposite. What is the opposite angle? Opposite of this angle. Opposite is IM all over hypotenuse. So, IN. You can also solve IM is equal to adjacent over hypotenuse. So, our cosine of adjacent, what is your adjacent? IC all over IN. So, that's it when R1 and X1 are neglected. When R1 and X1 are considered. So, again, nandito pa rin yung E1, E2. It is equal to V2 and the flux is perpendicular to E1, E2, and V2. The negation of E1 is at this direction, negative E1. Again, your IM is in phase with your phi or flux. So, nandito yung IM. Your IC is in phase also with E1. The sum of these two will be your IN and the current also flowing in R1 and X1 is the same current in IN because they are just in series. I1 is equal to 0. So what will be the drop in the resistance? So that will be equal to IN R1. The drop in X1 is IN X1. This is a resistive, so it is just the parallel of IN. So, nandito yung drop ng IN R1. It is just the parallel of IN because they are in phase. IN R1. And IN X1, X1 is an inductive. So, inductive means it is displaced by 90 degrees. So, nandito yung drop ng IN X1. So, this is 90 degrees. So, as we can see here in circuit diagram, V1 is equal to the drop in R1, X1, so that is IN, multiplied by R1 plus J X1, plus the drop in dito. So, that is plus IN multiplied by the parallel combination of these two. RC times JXM divided by RC plus JXM. As you can see, this quantity is equal to negative this one, negative E1. So the sum of negative E1 plus INR1 plus INX1 is equal to the input voltage. This will be your VI. Ito. That is your VI. And the angle between the no load current and VI or V1 input voltage is your angle theta. So, ito na lang. Angle between IN and V1 is angle theta, your power factor. So, no load power or input power or no load is equal to input voltage multiplied by no load current cosine angle theta. Okay, so you can also solve again IN using Pythagorean Theorem like what we did in here. IN is equal to square root of IM squared plus IC squared. So IM is equal to cosine of adjacent, which is IC, all over IN, and IC is equal to arc sine of opposite of the angle is IM divided by IN. We will use this one, the first one, when in the problem R1 and X1 are not given. Pag given yung R1 and X1, so ito yung gagamitin natin. Okay, let's have an example. Example number 1. The no-load current of a transformer is 4 amperes at 0.25 power factor when supplied at 250 volts, 50 hertz. The number of turns on the primary winding is 200. Calculate first the RMS value of the flux in the core. Assume sinusoidal flux. 2. The core loss, and 3. The magnetizing current. So we have here R1 and X1 are not given. So we will use the first one. The R1 and X1 are neglected. Our formula in primary voltage and secondary voltage is equal to E1 is equal to 4.44 from our generated voltage formula. E1 is equal to 4.44. F, flux multiplied by the number of turns. So flux, since this is in maximum, our formula is in maximum, and we are required to solve for the RMS value. So later na yun. Flux M is equal to E1. E1 is 250 volts divided by 4.44. times the frequency is 50 Hertz and number of turns is 200. That is equal to 5.631 milliweber. Flux RMS is equal to flux maximum divided by square root of 2. So 5.631 milliweber divided by square root of 2 equal to 3.981 milliweber. That is for letter I. Next, core loss. So, paano natin isosolve yung core loss? I-draw muna natin yung equivalent circuit diagram ng transformer without the R1 and X1. So, it will become just the parallel combination of this is RC, XM. This is your winding. The primary, secondary. Your secondary winding is open. So, nandito yung E1 mo. Induced EMF E1. And this is your input voltage, 250 volts. Since wala na yung R1, X1, this will be your no load current, IC and IXM. Paano natin isosolve yung IC? Because core loss power, in terms of power, PC is equal to IC squared RC, or the voltage at this point, at this branch. So what is the voltage at this branch? So it will be equal to your input voltage kasi they are in just parallel connection. So naka-parallel si RC sa input voltage. Also your XM is in parallel with the voltage, with the input voltage. The reading of the voltmeter at this point, at these nodes RC, will be 250. So it is equal to the input voltage V1 multiplied by the current IC. So walang RC kaya hindi natin ito magagamit. Ito yung magagamit natin to solve for the core loss. I-solve muna natin yung IC. So paano natin isosolve yung IC? So sa problem may given na no load current which is equal to 4 amperes. May no load current na 4 amperes and power factor equal to 0.25. So paano natin to i-draw sa vector diagram? So tapos niyo na to nung circuits 2 nyo. Okay? We can rewrite this one in terms of its magnitude and direction. So what will be the arc cosine of 0.25? The theta is equal to arc cosine of 0.25, that is equal to 522 degrees 522 degrees. So IN will be equal to 4 angle 75.522 degrees. From our vector diagram a while ago without the R1 and X1, This is our IM and IC. Also, our input voltage is in phase with IC. This is V1, input voltage. Our no load current is the sum of IC and IM vectorially. Nandito yung resultant niya na 4. And this angle is the power factor, so it is the angle between IN and the VI. Ito, angle theta. This is theta. So this is the power factor of V1 and IN. Paano natin isosolve yung IC? From SOHCAHTOA. So we can solve IC equal to cosine theta equal to adjacent. What is the adjacent? IC and hypotenuse divided by IN. So cosine theta again, eto ay 75.522. Again, cosine theta is 0.25 equal to IC unknown divided by 4. So IC is equal to 4 times 0.25 equal to 1 ampere. So 1 ampere yung IC. You can now solve your core loss. PC is equal to input voltage times IC. That is equal to 250 volts times 1. So you have 250 watts. Next, unknown is III, the magnetizing current, IM. Using Pythagorean Theorem, we can solve IM, di ba? Kasi alam na natin yung IC and given naman yung IN. IM is just the square root of IN square minus IC squared equal to square root of 4 squared minus 1 squared equal to square root of 15 amperes or 3.873 amperes. So don't forget to write these examples in your notebook. I will check all of your notes, yung mga examples, and dapat yung mga discussions sa mga videos na pinupost ko para naman may matira. Hindi nyo makalimutan pag nag-review na kayo. Okay, let's have another example. Number 2 example. A 2200/200 volts. So this is a step-down transformer. Draws a no-load primary current of 0.6 amperes and absorbs 400 watts. Find the magnetizing and iron loss currents. Letter B, a 2200/250 volts transformer takes 0.5 amperes at a power factor of 0.3 on open circuit. Find the magnetizing and working components of no-load primary current. Letter A given, we have primary voltage V1 is equal to 2,200 volts, and primary current, that is your no load IN, is equal to 0.6 ampere. And 400 watts, only the resistive component has a wattage. So this is your PC. The power loss in your windings, that is 400 watts. Find the magnetizing, that is your IM, and iron loss current, which is IC. So how will we solve this IM and IC? If we draw the circuit diagram, so hindi given yung R1 and X1, this is your resistance and inductance. At the primary, this is your winding. Nandito yung E1 mo. Ito yung secondary. This is your RC and XM. This is your IC and IM. Your input voltage, AC, which is equal to 2,200 volts. From here, we have no load current, IN. So, paano natin isolve yung IC? The voltage across this RC is equal to our input voltage, 2,200. And the power in this branch is 400 watts. So from our formula, PC is equal to V1 IC. So IC is equal to 400 watts divided by 2,200. That is equal to 0.182 amperes. So given na yung IC and IN natin, this will be our vector diagram. This is IM, IC, and the sum of these two is your IN. Pythagorean Theorem, we can solve your magnetizing current. IM is equal to the square root of IN square minus IC square. So IN is 0.6 ampere square minus 0.182 square root. That is equal to 0.572 amperes. So, ito yung unknown na isa. Tsaka ito yung isa. For letter B, 2,200 volts, 250 volts transformer takes 0.5 amperes at power factor of 0.3, an open circuit. So, may power factor siya. Find the magnetizing and working component of no load primary current. So, ang unknown ay yung IC and IM. Our IN is equal to 0.5 ampere and we have an open a power factor of 0.3. So theta is equal to our cosine of 0.3. Power factor natin is, di ba, cosine theta. So our cosine of 0.3 is, your calculator must be in degrees, 72.542 degrees. So if you will draw the vector diagram of this, we have unknown yung IM and IC. Yung IN yung given, which is equal to 0.5. And the theta here is equal to 72.542. So we can solve this one using SOHCAHTOA. So IC is equal to, letter A given, we have primary voltage V1 is equal to 2,200 volts, and primary current, that is your no load IN, is equal to 0.6 ampere. And 400 watts, only the resistive component has a wattage. So this is your PC. The power loss in your windings, that is 400 watts. Find the magnetizing, that is your IM, and iron loss current, which is IC. So how will we solve this IM and IC? If we draw the circuit diagram, so hindi given yung R1 and X1, this is your resistance and inductance. At the primary, this is your winding. Nandito yung E1 mo. Ito yung secondary. This is your RC and XM. This is your IC and IM. Your input voltage, AC, which is equal to 2,200 volts. From here, we have no load current, IN. So, paano natin isolve yung IC? The voltage across this RC is equal to our input voltage, 2,200. And the power in this branch is 400 watts. So from our formula, PC is equal to V1 IC. So IC is equal to 400 watts divided by 2,200. That is equal to 0.182 amperes. So given na yung IC and IN natin, this will be our vector diagram. This is IM, IC, and the sum of these two is your IN. Pythagorean Theorem, we can solve your magnetizing current. IM is equal to the square root of IN square minus IC square. So IN is 0.6 ampere square minus 0.182 square root. That is equal to 0.572 amperes. So, ito yung unknown na isa. Tsaka ito yung isa. For letter B, a 2,200 volts, 250 volts transformer takes 0.5 amperes at a power factor of 0.3, an open circuit. So, may power factor siya. Find the magnetizing and working component of no load primary current. So, ang unknown ay yung IC and IM. Our IN is equal to 0.5 ampere and we have an open power factor of 0.3. So theta is equal to our cosine of 0.3. Power factor natin is, di ba, cosine theta. So, our cosine of 0.3 is, your calculator must be in degrees, 72.542 degrees. So, if you will draw the vector diagram of this, we have unknown yung IM and IC. Yung IN yung given, which is equal to 0.5. And the theta here is equal to 72.542. So we can solve this one using SOHCAHTOA. So IC is equal to adjacent hypotenuse. Cosine adjacent is IN cosine theta and IM is, ito yung IM mo, IN sine theta. Opposite hypotenuse. So IC is equal to 0.5. Cosine theta is, ano yung power factor? Power factor ay 0.3. So, 0.5 times 0.3, 0.15 ampere. Next, IM is equal to IN. 0.5 times sine of what? Sine theta is 72.542. So, IM is equal to 0.47697 amperes. Or you can solve IM using Im is equal to square root of In squared minus Ic squared. So, square root of 0.5 squared minus 0.15 squared equal to 0.47697 amperes.